Turning our attention to Chapter 5, Scaling Principles, Latency, Throughput, and State Management. Let's discuss theoretical foundations. The theoretical foundation for deploying containerized AI agents at scale rests upon three pillars: elastic scaling, state persistence, and throughput optimization. In a cloud-native environment, an AI agent is not a static executable, it is a dynamic service that must react to fluctuating demand while maintaining conversational context and minimizing inference latency. This requires moving beyond simple container orchestration to a sophisticated interplay of runtime metrics, distributed data structures, and memory management techniques. Now, let's explore the analogy, the high-volume restaurant kitchen. To understand these concepts, consider a high-volume restaurant kitchen during the dinner rush. 1. The agent pod. The chef. A single instance of an AI agent running in a container is like a chef. The chef has a limited capacity to process orders, inference requests. 2. Horizontal pod autoscaling, HPA. The kitchen manager. The manager watches the chefs. If the queue of orders grows or the chefs are sweating high GPU/CPU usage, the manager hires more chefs, scales out pods. If the rush ends, the manager sends chefs home, scales in, to save money, resources. 3. Distributed caching. The recipe book and prep station. A chef cannot remember every order for every table perfectly while cooking. They rely on a shared recipe book, distributed cache like Redis, and a prep station where ingredients are prearranged. If Chef A starts a complex sauce for table 5 but gets reassigned, Chef B can step in, look at the prep station, cache, and continue without starting over. 4. Request batching. The plating station. Instead of plating one dish at a time as soon as it's ready, the kitchen gathers several dishes that finish at similar times and plates them together in one swift motion. This reduces the number of trips to the pass, GPU memory bandwidth, and maximizes the use of the garnish spoon, compute cycle. Turning our attention to horizontal pod autoscaling, HPA, and custom metrics. Standard HPA in Kubernetes typically scales based on CPU or memory usage. However, for AI agents, these are poor proxies for load. A GPU might be at 100% utilization processing a single, massive batch of requests, or it might be idle waiting for a network response. Why custom metrics matter? In AI inference, the true bottleneck is often the queue depth of requests waiting for the GPU or the GPU memory allocation. We need to scale based on the metric that directly correlates with the agent's ability to respond, inference latency or GPU utilization. The C# context. While C# does not natively manage Kubernetes HPA configurations, it is the language of the agent's runtime environment. The agent must expose these metrics to the Kubernetes metrics server. In modern .NET, this is achieved using system diagnostics metrics, introduced in .NET 6, which provides a high-performance, low-allocation API for emitting metrics. We use an iMeter to track the time to first token, TTFT, or tokens per second, TPS. If the average TTFT exceeds a threshold, e.g., 500 milliseconds, the C# application emits a custom metric. An adapter, like Prometheus, scrapes this metric, and the HPA controller uses it to calculate the replica count. We begin by importing necessary namespaces. System diagnostics provides classes to trace the execution of our application, which is fundamental for observability. System diagnostics metrics is particularly crucial here as it introduces the modern .NET API for collecting and publishing metrics, a cornerstone of cloud-native monitoring. This allows us to instrument our code to understand its performance and behavior in production environments, which is vital for maintaining healthy microservices. Here, we declare the inference metrics class. This class is designed to encapsulate all the metrics related to our AI agent's inference process. By centralizing metric definitions and recording logic, we ensure consistency and make it easier to instrument our AI agent. This separation of concerns is a good practice, promoting cleaner code and easier maintenance, especially in complex microservice architectures where many different metrics might be collected. Notice this line, private static read-only meter_meter equals new, AI, agent, inference. We instantiate a meter object, which acts as the factory for all instruments, like histograms and gauges, within our application. The name AI agent inference is critical. It uniquely identifies this set of metrics, allowing monitoring systems, like Prometheus or OpenTelemetry collectors, to distinguish metrics from different services or components. Making it static ensures that only one meter instance exists across the entire application domain, which is an efficient way to manage metric sources and avoids resource duplication, particularly important in resource-constrained container environments. At lines 9 to 14, we define a histogram double named _generation latency. This instrument is specifically chosen to track the distribution of generation latencies. Histograms are incredibly powerful because they don't just give us an average, they allow us to see percentiles, e.g., 90th, 99th percentile, which are far more informative for understanding user experience. A high average latency might hide the fact that a small percentage of requests are experiencing extremely long latencies. The units, ms, and the description, time taken to generate a response, provide crucial context for anyone interpreting these metrics, making our observability data actionable. Next, we define an observable gauge int named _QDepth. Unlike a histogram, which records events, a gauge reports the current value of a metric at a given point in time. The observable prefix is key here. It means the gauge's value is determined by a callback function, equals request queue, count, which is executed periodically by the metric system. This design is perfect for capturing dynamic values like the number of requests currently waiting in a queue. Monitoring queue depth is vital for understanding back pressure and potential bottlenecks in our AI agent, especially when managing GPU resources in a containerized environment. A consistently high queue depth indicates that our agent might be under-provisioned or struggling to keep up with demand, signaling a need for horizontal scaling. Finally, we have the record latency method. This public method provides a clean, encapsulated way for other parts of our application to record a generation latency. When an AI model finishes processing a request, it will call this method, passing the elapsed time. This separation ensures that the core logic of the AI agent doesn't need to know the specifics of metric instrumentation, adhering to the principle of loose coupling. This method simply delegates the recording to our _generation latency histogram, ensuring that all latency measurements are consistently captured by our observability system. Architectural implication: by decoupling the scaling trigger from generic CPU usage to domain-specific metrics, latency/queue depth, we achieve intent-based scaling. The system scales not because the CPU is busy, but because the user experience is degrading. This requires a deep integration with the .NET Runtime's instrumentation capabilities. Moving on to distributed caching for agent state. AI agents are inherently stateful during a session. A conversation requires context, previous messages, tool outputs, memory. However, in a horizontally scaled environment, a user's request might land on pod A, while their next request lands on pod B. If pod A crashes or scales down, the conversation history is lost if it resides solely in that pod's RAM. The problem of ephemeral state: containers are ephemeral. Relying on in-memory cache or static variables for session state is a critical failure point in distributed systems. We need a mechanism to externalize state so that any pod can pick up a conversation exactly where the previous one left off. The solution: distributed caching, Redis/Memcached. We treat the distributed cache as the short-term memory of the agent cluster. The C#I distributed cache interface abstracts the underlying storage provider, allowing us to swap between Redis, SQL Server, or Ncache without changing the agent logic. Why C# interfaces are crucial here. In Book 6, we discuss dependency injection, DI, and interfaces. We defined an iConversation store. In this chapter, we implement that interface using iDistributed cache. This allows us to inject a Redis-backed implementation in production and a memory-backed implementation in unit tests. Serialization and memory efficiency: storing complex agent state, which might include system, text, JSON objects or binary tensors, requires efficient serialization. .NET 8 introduced system, text, JSON source generators, which allow for high-performance, reflection-free serialization. This is critical because the overhead of serializing/deserializing state on every request can negate the benefits of caching. At the very top, we're bringing in essential namespaces. Notice Microsoft, extensions, caching, distributed at line 1. This is crucial for enabling our application to use a distributed cache, like Redis. This design choice is fundamental for cloud-native applications because it allows our agent state to be stored externally, making the agent itself stateless. This statelessness is key for horizontal scalability, as any instance of our agent can serve any request without needing to hold session-specific data in its own memory. System, text, JSON at line 2 and system, text, JSON, serialization, metadata at line 3 are for efficient JSON serialization and deserialization, which we'll use to convert our agent state to and from byte arrays for storage. Here, from lines 5 to 9, we define the iAgent state store interface. This interface establishes a contract for how our agent state will be managed. It declares two asynchronous methods, getStateAsync to retrieve state and setStateAsync to persist it. Using an interface like this is a best practice for dependency inversion. It decouples the business logic, the agent, from the persistence mechanism, the state store. In a cloud-native context, this means we could easily swap out Redis for another distributed cache technology, like Azure Cache for Redis or AWS Elasticache, without modifying the agent's core logic. This flexibility is vital for adapting to different cloud environments and optimizing costs or performance. Now, let's look at lines 11 to 18, where we introduce the Redis Agent State Store class, which implements our iAgent State Store interface. This class is specifically designed to use Redis as its backing store for agent state. The private read-only iDistributed cache_cache declaration at line 13 is where we hold an instance of the distributed cache. The constructor, from lines 15 to 18, takes an iDistributed cache instance as an argument. This is a prime example of constructor injection, a core principle of dependency injection. It means that Redis Agent State Store doesn't create its own iDistributed cache but rather receives it from the dependency injection container. This makes the class testable and allows us to configure the distributed cache, e.g., pointing it to a specific Redis instance, externally, which is crucial in a microservices architecture where configurations often change per environment. Moving on to lines 20 through 28, we have the getStateAsync method. This method is responsible for retrieving the agent state from the distributed cache. At line 22, await_cache.getAsync, session ID, CT, attempts to fetch the raw byte data associated with a given session ID. If no data is found, line 23, it returns the default value for the type T. The interesting part is at line 27, JSON serializer, deserialize, data, typeof, T, as T. Here, we're deserializing the byte array back into our agent state object. The comment at lines 25 to 26 highlights the use of source generators. This is a modern performance optimization in .NET. Instead of using reflection at runtime, which can be slow and memory-intensive, especially in hot paths, source generators create the serialization/deserialization code at compile time. This results in zero reflection deserialization, significantly improving performance and reducing startup time, which is highly beneficial for cloud-native applications where rapid scaling and efficient resource usage are paramount. Finally, let's examine lines 30 through 40, which define the setStateAsync method. This method handles persisting the agent state to the distributed cache. At line 32, byte, data equals JSON serializer.serialize to UTF-8 bytes, state, converts the agent state object into a UTF-8 byte array. Again, system, text, JSON is used for efficient serialization. From lines 34 to 37, we create distributed cache entry options. Notice the sliding expiration equals time span. From minutes, 30, at line 36. This is a critical configuration for managing cache memory and ensuring data freshness. A sliding expiration means that if the session is accessed within 30 minutes, its expiration time is reset. If it's not accessed for 30 minutes, it's evicted from the cache. This prevents stale data from accumulating and frees up valuable cache resources, aligning perfectly with cloud-native principles of efficient resource management. Lastly, at line 39, await_cache.setAsync, session ID, data, options, CT, stores the serialized state in Redis with the specified expiration policy, completing the state persistence cycle. Architectural implication: by externalizing state, we enable stateless pods. The pods contain only the logic and the loaded AI model waits, the data flows in and out. This allows for aggressive scaling. If a pod becomes unresponsive, the Kubernetes controller terminates it, and the next request simply retrieves the state from the cache and initializes a new pod. This pattern is essential for high-availability AI agents. Moving on to request batching and memory management. AI models, particularly large language models, LLMs, are computationally expensive. The cost of a single inference is dominated by memory bandwidth and matrix multiplication. Processing requests one by one, synchronous processing, leaves the GPU underutilized because memory access patterns are not optimized. The concept of batching involves collecting multiple inference requests and processing them simultaneously in a single forward pass of the model. Static batching, grouping requests that arrive within a fixed time window. Dynamic batching, grouping requests of varying lengths, token counts, efficiently to maximize GPU utilization without exceeding memory limits. The C# context, system, threading, channels. In C#, we use system, threading, channels to implement a producer-consumer pattern for request batching. This is a modern, high-performance alternative to blocking collection or concurrent queue. 1. The producer, the HTTP endpoint, receives a request. Instead of calling the model immediately, it writes the request, payload plus completion source, into a channel. 2. The consumer, a background service in .NET, reads from the channel. It accumulates requests until a threshold is met, e.g., batch size equals 32, or timeout equals 10 milliseconds. 3. The batcher, Once the threshold is met, the consumer takes the batch, formats the input tensors, and sends them to the inference engine, e.g., ONNX runtime, Torch Sharp, or an external Python process via gRPC. Why channels? Channels are async-ready and highly efficient. They handle backpressure automatically. If the consumer is slow, GPU is busy, the channel's internal buffer fills up, and the producer's write operation awaits, naturally throttling the incoming HTTP requests without crashing the server. We begin by importing the system, threading, channel's namespace. This is crucial because it provides the channel primitive, which we'll use as a robust, thread-safe, asynchronous queue for managing incoming inference requests. The batching service class itself is declared, serving as the central orchestrator for collecting and processing these requests in batches. Notice how this class encapsulates the core logic for batching, making it a self-contained component, a common practice in microservices architecture for clear separation of concerns. Here, we declare two private, read-only fields, _channel and _model runner. The _channel, initialized in a constructor, is where incoming inference request objects will be temporarily stored. The _model runner, injected via the constructor, represents the component responsible for actually executing the AI model. This dependency injection pattern, where model runner is passed in, promotes loose coupling and testability. We're setting up a channel with a bounded capacity of 1,000 requests. This is a critical design choice for cloud-native applications. A bounded channel prevents memory exhaustion if requests arrive faster than they can be processed, effectively applying backpressure. If the channel is full, new writes will wait, as specified by bounded channel full mode, wait, pausing the producers rather than consuming all available memory, which is vital for maintaining container stability under load. The enqueueasync method provides the public interface for adding new inference request objects to our batching system. It's an async value task method, indicating that the operation might involve an asynchronous wait, but it's designed to be allocation-free when the operation completes synchronously. We simply write the incoming request to the _channel writer. Because our channel is bounded and configured to wait when full, this write async call will automatically apply backpressure. If the inference pipeline is overloaded, incoming requests will pause here, preventing the service from crashing due to excessive memory usage, which is a key consideration for resilient cloud deployments. The process batches async method is the heart of our batch processing loop. It's an async task that takes a cancellation token. This token is crucial for graceful shutdown in a cloud environment. It allows the host to signal that the service should stop processing, ensuring that long-running operations can be cleanly terminated. We use a wait for each to consume batches from the readBatches async method. This construct is powerful for asynchronously iterating over sequences. Once a batch is retrieved, we delegate its execution to _modelrunner.executeBatchAsync. This separation of concerns means batching service focuses solely on batch formation, while model runner handles the actual, often computationally intensive, model inference, likely on a GPU. This modularity improves maintainability and allows for independent scaling or optimization of each component. Now we delve into the readBatches async method, which is an async async enumerable read-only list inference request. This signature indicates that it will asynchronously yield batches of requests. We initialize a list inference request with a capacity of 32, anticipating our target batch size. This pre-allocation helps reduce reallocations as items are added, improving performance. We also set up a timer using task delay for a short duration, 10 milliseconds. This timer is critical for our latency optimization strategy, allowing us to send smaller batches if a full batch isn't formed quickly. The wait for each loop then continuously reads individual requests from the _channel reader, adding each one to our batch list. Here, we define the two conditions under which a batch is yielded for processing. First, at line 43, if batch count equals 32, we've reached our desired batch size. We yield return batch, sending it off for inference, and then reset batch and timer to start collecting a new one. This maximizes throughput by ensuring the GPU is fed with optimally sized chunks of work. Second, at line 49, if the batch isn't full but the timer has expired, meaning 10 milliseconds have passed since the last batch was started or reset, we yield return batch even if it's smaller. This is a crucial latency optimization. We're trading off some potential throughput, by not waiting for a full batch, for lower end-to-end latency, which is often a critical requirement for real-time inference services. The task.whenAny timer, task.completedTask, ensures we don't block indefinitely waiting for the timer if task.completedTask is already done, making the check efficient. This dual condition, batch size or timeout, is a common pattern for efficient batching systems, balancing throughput and latency. Architectural implication, batching transforms the cost curve of inference. By increasing throughput per GPU cycle, we reduce the number of pods required to handle the same load, directly impacting cloud costs. However, it introduces latency variance. A request arriving just after a batch is dispatched must wait for the next batch. This is a trade-off between throughput, requests per second, and latency, time to first token. Now, let's talk about integration, the complete picture. These three concepts form a feedback loop. 1. Traffic enters and is enqueued via system, threading, channels, batching. 2. The batching service groups requests and retrieves agent state from the iDistributed cache, Redis. 3. The model processes the batch. The inference metrics meter records the latency. 4. The HPA controller reads the custom metric, e.g., agent.generation.latency.ms. If latency spikes, it scales out the number of pods. 5. New pods start up, connect to the same Redis cluster, and immediately begin processing from the shared queue. Moving on to theoretical foundations. By leveraging modern C# features like system, threading, channels for backpressure management, iDistributed cache for state abstraction, and system, diagnostics, metrics for observability, we transform a simple AI model into a resilient, cloud-native service. The theoretical goal is to decouple the lifecycle of the compute resources, pods, from the lifecycle of the user session, state, allowing them to scale independently based on real-time demand signals. Let's discuss basic code example. Here is a simple, self-contained C# example demonstrating a request batching pattern for an AI inference service. This pattern is fundamental for optimizing resource usage, GPU/CPU, in containerized environments, as it allows aggregating individual requests into a single batch to maximize hardware parallelism. We begin by importing necessary namespaces from the .NET framework. Notice system, collections, concurrent, line 2, which is crucial for thread-safe data structures, especially for our request queue. System, threading, line 6, and system, threading, tasks, line 7, are fundamental for asynchronous operations and managing concurrency, which is a cornerstone of efficient cloud-native services. These imports lay the groundwork for building a responsive, non-blocking inference engine. Here, lines 9 to 16, we define the cloud-native AI, microservices, inference namespace, organizing our code logically. Immediately after, we introduce the inference request class. This class acts as a container for a single incoming inference request. It's generic, t-input, t-output, to allow flexibility in the types of data our AI model can handle. This design promotes reusability and type safety, which are good practices in any robust system. Inside inference request, lines 17 to 21, we have two key properties, input and completion source. The input property holds the actual data to be processed by the AI model. The completion source is a task completion source, t-output. This is a powerful .NET construct that allows us to create a task that can be completed at a later time. This pattern is vital for decoupling the request submission from its processing, enabling asynchronous communication and allowing the client to await the result without blocking. This section, lines 23 to 28, introduces the inference engine class, which is the core component of our batching system. The XML comments clearly state its purpose, to simulate an AI model inference engine that processes requests in batches. This is a critical cloud-native pattern for AI workloads. Why batching? Because AI models, especially deep learning models, are often optimized for parallel processing on GPUs, and processing multiple inputs simultaneously, a batch, is significantly more efficient than processing them one by one. This reduces overhead and maximizes hardware utilization. We declare the private fields for inference engine here, lines 29 to 37. Underscore request queue, line 29, is a blocking collection, which is a thread-safe, blocking queue that will hold our incoming inference request objects. Underscore batch size and underscore batch timeout lines 30 to 31, define the batching strategy. Underscore cancellation, line 32, is for graceful shutdown, and underscore processing task, line 33, will hold the background task that continuously processes batches. Finally, underscore model inference func, line 36, is a func delegate that represents the actual AI model's computation, allowing us to inject different model implementations. The constructor for inference engine, lines 38 to 43, initializes the batching parameters and the model inference function. Notice how underscore batch size, underscore batch timeout and underscore model inference func are set directly from the constructor arguments. This dependency injection approach makes the inference engine highly configurable and testable. We're not hard-coding the batching logic or the model, which is excellent for adaptability in a microservices environment where these parameters might change based on workload or model updates. Crucially, in lines 44 to 50 of the constructor, we initialize underscore request queue with a bounded capacity of 1000. This is a vital cloud-native consideration. Without a bounded capacity, an unbounded queue could consume all available memory if requests arrive faster than they can be processed, leading to an out-of-memory exception and a crash. A bounded queue provides backpressure. If the queue is full, _request queue, add, would block, signaling to upstream services that the engine is overloaded. This prevents resource exhaustion and helps maintain stability. We also start the _processing task immediately, kicking off the background batch processing loop. The infer async method, lines 52 to 56, is the public API for submitting an inference request. It takes an input and returns a task T output. This asynchronous signature is fundamental for a responsive microservice. Clients can call infer async without blocking their own threads, allowing them to perform other work or serve other requests while waiting for the AI model's result. This is a key aspect of non-blocking I/O and efficient resource utilization in a cloud environment. Inside infer async, lines 57 to 68, we create a new task completion source T output, line 57. This TCS will be used to signal the completion, or failure, of this specific inference request. We then wrap the input and the TCS into an inference request object, lines 58 to 62. Finally, we add this request to the _request queue, line 65. The blocking collection, add method is thread safe. The client immediately gets back TCS, task, line 67, which they can await. This effectively hands off the processing to the background _processing task and provides an asynchronous handle for the result. The process batches async method, lines 70 to 74, is the heart of our batching logic, running continuously in a background task. It's an async task method, allowing it to perform non-blocking waits. The while token.is cancellation requested loop ensures that this processing continues until a cancellation signal is received, enabling graceful shutdown. This pattern is common for long-running background services and microservices, ensuring they can be stopped cleanly without losing in-flight requests or corrupting state. At lines 76 to 81, within process batches async, we attempt to take the first request from the _request queue. We use _request queue.tryTake with a timeout, timespan. For milliseconds, 100. This is a non-blocking wait that allows the loop to periodically check for cancellation, rather than blocking indefinitely. If no request arrives within the timeout, tryTake returns false, and the loop continues, checking the cancellation token again. This ensures responsiveness during idle periods and proper shutdown behavior. Once a first request is successfully taken, line 83, we initialize a new batch list with this request. We also start a stopwatch, line 84. The stopwatch is crucial for implementing the _batch timeout logic, allowing us to measure how long we've been trying to fill the current batch. This combination of a minimum batch size and a maximum timeout is a common strategy to balance latency and throughput for AI inference. We want to fill batches for efficiency, but not wait too long, causing high latency for individual requests. This while loop, lines 87 to 94, is where the batch filling happens. It continues as long as two conditions are met: the batch count is less than _batch size and the SW elapsed milliseconds is less than _batch timeout. Inside the loop, _request queue.tryTake is called again, but this time with a shorter timeout, 10 milliseconds. This allows us to quickly gather more requests if they are available without blocking for a long time. If a request is found, it's added to the batch. This dynamic batching ensures that we either hit our desired batch size or process what we have within the timeout, optimizing resource usage. After the batch filling loop completes, either because the batch is full or the timeout has elapsed, we call await execute batch async, batch, line 97. This offloads the actual model inference to another asynchronous method. By await ing it, the process batches async method will pause until the batch inference is complete, but it won't block the underlying thread. This allows the system to remain responsive and potentially handle other tasks if the execute batch async method itself involves I/O or other asynchronous operations. The execute batch async method, lines 101 to 107, is responsible for performing the actual AI model inference. We start with a try-catch block to handle potential exceptions during inference, ensuring that errors are propagated back to the callers. Inside the try block, we first extract the input data from all requests in the batch, line 106. This creates a list of inputs suitable for passing to a batched AI model, which expects multiple inputs simultaneously for efficiency. At lines 108 to 114, we simulate the core AI model processing. Await task, delay, 50, line 109, simulates network latency or the time it takes to transfer data to a GPU, which is a common overhead in real-world inference. The crucial part is var results equals _model inference func, inputs, line 113. This is where the actual AI model computation would occur. In a real containerized scenario, this function would invoke a TensorFlow.net, Torch.net, or ONNX runtime model. This is also where significant GPU memory and compute resources would be utilized. Batching helps amortize the fixed costs of model loading and invocation over multiple inferences. After the underscore model inference func returns the results for the entire batch, lines 115 to 119, we iterate through the original batch of inference request objects. For each request, we use its completion source.trySetResult, results, I, to complete the task that was returned to the client. This effectively delivers the specific output to the client who made the original request. TrySetResult is used because the task might have already been cancelled or completed by other means, preventing exceptions. The catch block, lines 120 to 128, handles any exceptions that occur during the batch inference. If an error occurs, it's critical to propagate this error back to all clients whose requests were part of the failed batch. We achieve this by iterating through each REQ in the batch and calling REQ completion source.trySetException, X. This ensures that clients waiting for a result will receive an exception, rather than hanging indefinitely, providing proper error handling and client feedback. The stop method, lines 130 to 136, provides a mechanism for graceful shutdown of the inference engine. First, underscore cancellation, cancel, signals the process batch's async loop to terminate. Then, underscore request queue.complete adding, tells the blocking collection that no more items will be added, which is important for the processing loop to eventually exit cleanly. Finally, underscore processing task, wait, blocks until the background processing task has finished. This ensures that all pending requests are either processed or properly handled before the engine fully shuts down, preventing data loss or orphan tasks. We enter the main method, lines 140 to 147, which serves as our entry point and demonstration. The console.writeLine confirms the demo's start. This section sets up the inference engine instance. Notice the generic parameters is string, indicating our model will take string inputs and produce string outputs for this demo. This highlights the flexibility of the generic design. The next few lines will configure the engine's crucial batching parameters. Here, lines 148 to 156, we initialize our inference engine. We set batch size, 4 and batch timeout temps, 200. These parameters are critical for performance tuning in a cloud-native environment. A larger batch size generally means higher throughput but potentially higher latency for individual requests. A shorter timeout means lower latency but potentially lower throughput if requests are sparse. The model inference func is a simple lambda that simulates AI processing by printing a message and prepending processed to each input. In a real scenario, this would be the invocation of a pre-trained AI model. This section, lines 158 to 162, begins simulating concurrent client requests. We create a list task to hold the asynchronous operations. The for loop iterates 10 times, representing 10 different clients or requests. Each iteration launches a new task, run, line 162, which executes asynchronously on a thread pool thread, mimicking real-world concurrent client interactions with a microservice. This highlights how the inference engine is designed to handle multiple incoming requests simultaneously. Inside each client's simulated request, lines 163 to 172, we measure the elapsed time using a stopwatch to demonstrate the latency experienced by individual clients. Await engine.inferasync, $input_ID, is the key line, line 168, where the client submits its request to the inference engine and asynchronously waits for the result. The console.writeLine statements provide visibility into when requests are sent and when their results are received, along with the measured latency. This helps us observe the effects of batching on individual request timings. At lines 173 to 176, we introduce a small await task, delay, 20, after each client request submission. This delay is intentional, it staggers the request slightly. Without it, all 10 requests would hit the underscore request queue almost simultaneously, likely forming one large batch immediately. By staggering them, we can better observe the batching behavior where requests might arrive over a period, allowing the engine to collect a partial batch if the timeout is reached before the batch size. Finally, at lines 178 to 183, await task.when all tasks ensures that the main method waits for all simulated client requests to complete before proceeding. After all requests are processed, engine stop is called. This triggers the graceful shutdown mechanism we discussed earlier, ensuring that the background processing task is terminated cleanly. The final console.writeLine confirms the demo's completion. This clean shutdown is crucial for cloud-native applications, as containers can be stopped at any time, and resources need to be released properly. Thank you for your attention. This lesson is excerpted from Volume 7, Chapter 5 of the C# and AI Masterclass ebook series and from the volume Cloud Native AI and Microservices, Containerizing Agents and Scaling Inference. You can find all the details here, https://github.com/edgarmilvas/C# programming series. The ebook also includes diagrams, advanced examples, and 5 exercises with solutions for every chapter. There are 26 chapters. If printed, it would exceed 600 pages. Subscribe to the channel to watch more videos. I look forward to seeing you in the next lesson.